Welcome everybody to Wireless Communications Alliance event. This is part of a series of Connected Everything focusing on hardware security attacks. We're going to show a demonstration of side channel attacks and a conversation about strategies to solve these problems. My name is Jeremy Toll. I'm the Vice President of the WCA. My contact information are on the screen. WCA is a organization, the nonprofit business league founded in 1994, dedicated to collaboration in the wireless industry worldwide, and our mission is to network people. We'd like to thank our sponsors, Asbill, Google, CIG, ETI, and others for their generous donations to the cause of and the mission of WCA. We are looking for additional sponsors, so if you find this event and other events that we do useful, we'd appreciate having a conversation with you on how we can create some more value. Our generous donations to the cause of our website is www.wca.org. Sponsors, so if you find this event and other events that we do useful, we'd appreciate having a conversation with you on how we can create some more.
Sir, would you please switch off your video and your audio?
Our website is I'm getting okay. I was getting a feedback in there. So our upcoming events include some annual events such as IoT Gizmos and Gadgets, which is a Oktoberfest theme, and we thought that we may be able to do an in-person event, but at this point we're going to keep this virtual. So we're going to have to all have our own fermented beverages at home, but that's on September 23rd. Open Wi-Fi is about the next Wi-Fi revolution, October 21st. What's Hot, What's Not is an event with investors and VCs and private equity people doing predictions and review of the year's events in wireless. That's in November 18th. We're going to do a global wireless startup pitch event on December 16th. And we have an annual event on Spectrum for 5G in January of 2022, and also an annual event on 6G/terahertz on February of 2022. So we're almost there. Some housekeeping. Please use, if you have questions, please use the Zoom Q&A question or even the comments section for questions. We plan to do the presentation and demo straight through and take questions at the end, but we'll be monitoring that and feeding it into our moderator. Also, the presentations and recordings will be available within 48 hours of the event. And we'd like to make greetings to the world and thanks for being our guests. Also, towards the end of the event, we're going to do a raffle of this nifty multi-tool hammer, which is a 14-in-1 accessories, outdoor camping, survival, functional tools, which is exactly what you need to tackle problems in the wireless industry. So you need to be present to win, and we'll do that towards the end of the event. And without further ado, we'd like to introduce Tom Willey as our moderator. He's a managing partner at TW Partners, and Hugh Diebold, the CEO of eShard, and they're going to be taking it from here. So Tom.
Okay, thanks, Jeremy. So I've been in the Bay Area about 30 years, and the first company that I worked with was a company called Silink, who did encryption, and that was where I kind of started to understand, how encryption all operated, basically how it worked. And since then, I've been working in the semiconductor industry, and mostly in the wireless space, mostly Wi-Fi, cell phones, and I thought encryption had solved all the security problems in the industry. But what I learned, and a little bit to my shame, what I learned about 2 or 3 months ago gave me an epiphany, is the best way of describing it. It turns out, and some of you guys may know this, but it turns out what had been solved by regular encryption and regular, encrypting blocks and chips is what I would call intended emissions. But there's a whole field of unintended emissions. And to give you the analogy that was put to me is way back when they used to have safes with a lock, so the burglar could pick the lock. And then they came up with these combination locks that had a large number of possibilities, and it would be impractical to try and figure out all the combinations. But people figured out if you put a stethoscope on the side of the safe, you could listen to the clicks and figure out what was going on. Now, those clicks are an unintended emission. And where my epiphany was looking at, cell phones, IoT devices, chips with encryption, you can monitor power, you can monitor electromagnetic radiation, and they're the same. And what's really special is people can run their magic and figure out how to break into those chips. And for me, that was an epiphany because everything fell into place about encryption. Now, the epiphany came from eSharp. And with me here is Hugues Thibault, who's Jeremy said is the CEO of eSharp. Now, Hugues has been working in this space a long time, and with eSharp, they specialize in helping companies improve security. And I've asked Hugues to come along and do a presentation to demo how I'll say easy, it's never totally easy, but how easy it is to break into IoT devices using things like unintended emissions. And at this point, I'm going to pass over to Hugues, and off you go. Thank you.
Okay, can you hear me? Good evening, good morning, good afternoon, good evening to all of you. I hope that you can see my screen now. Can you see my presentation?
Yes.
Yes.
Excellent. So I'm very glad to be there today, even if it's a bit late for me. I'm still there, and I'm going to talk to you about hardware security attacks today. So who am I? I am Hugues Thibault, CEO and founder of eSharp, and I have been working in such chain fault injection for almost 20 years. Okay, so I have been doing practical attacks, and I have been working on the different protections to make sure that actually some devices could withstand attacks. And I have also an experience as a lab director because I was working for Underwriters Laboratory, where I was supervising all the security evaluation of payment devices. Okay, but I have been talking too much about me. I think you're here to know about such an attacks. So it's a physical attack. So my point is today to say, when it's about an IC, you have millions of devices on the field, right? If I tell you that it only takes a few minutes to hack it, it looks impossible, right? It's unacceptable. But it's particularly unacceptable because in the IC, you have cryptography that is managed in a secure system. And cryptography is all about secret keys. If the cryptography is adhered, you don't want this to be compromised. And actually, such channel attack techniques can compromise your cryptographic keys in a few minutes. So I'm here today to explain to you that, yes, it is genuinely a few minutes, if it's not protected, obviously, and that it should be taken into account. So if I do well, this will look like an obvious thing at the end of this talk. Okay. So some of you may wonder what is a side chain? What is a side chain? Okay, so I will try to explain it very simply. First, here our assumption is you have a device. On this device, you have a chip, an IC. And in the IC, you have cryptography. So if there is cryptography, this means that somewhere there is a secret key on the same device. And this device will operate the cryptographic operation using this key. Obviously, the key is your asset, and you don't want this key to be exposed. This is the whole thing. So an American guy a few years ago, in 1996 precisely, said that actually, even though the cryptographic algorithm is deemed as secure, resistant against a mathematical attack, if you can collect little bit of information during the internal execution of the algorithm, you may retrieve the key. So the whole purpose of side channel is actually to get and to extract this information from the chip when it operates the cryptographic algorithm. And maybe in this information, there will be information about the intermediate data of the cryptographic execution, and that could be useful for the attacker. So what kind of signal can you get? How can you get this little information about intermediate data? By simply exploiting what we name side channel. Okay, actually, this is all these different pieces of information you can get in a side way. So one example is a power fluctuations when the cryptographic algorithm is being processed. Okay, it's a bit, if I monitor your heart when you are running.
Please allow interruption. Your voice is breaking up. Can you please put the microphone a little bit lower from your nose, more to your mouth, a little bit lower to your mouth?
Like this?
Thank you so much. Yeah.
Yeah, it's okay. So it's a bit like your heartbeat. When you are running, your heart is quite fast, okay? And when you're sleeping, it's slow. So if I am able to monitor your heart, I know what you're doing. It's exactly the same thing with such channel. And at the end, you will extract plenty of signal from plenty of different execution you will run, always with the same key, but with different inputs. Okay, this is this kind of signal. And after that, by applying some signal processing and statistics, these little informations that you have in the signal will lead you to the secret key. Okay, so I'm going to explain this further today. But this is a principle in a few words. So is it a real risk? Actually, if the device is not protected, as I said before, it only takes a few minutes. So it can be very fast. Okay, let's say around 1 hour if you want. Okay, it's not 2 minutes, but it's around 1 hour, but still super fast. Okay, and after that, it's up to you to see with your system how harmful it is for your system if the secret key is compromised. So you need to make this what we name vulnerability analysis. Okay, so I try to give you some real attacks that happened over the past years, okay, quite recently. So one recent attack concerned Google Titan security. So you can Google it, it's clear. So actually there are two researchers. They managed to break a signature, so a cryptographic signature. So it was an elliptic curve algorithm, and they managed to retrieve the full elliptic curve key, secret key. So this means that they could compromise the signature of the device. A second example. So this one was published in January 2021. So it's a recent work. Another one is even more recent. Actually, there is a conference named Chase, okay, that will take place in a few days now. And this paper is going to be presented at this conference. It's about a side channel compromising an FPGA. And for that one, it targets an AES, which is a symmetric algorithm. Okay, they managed to partially find the secret AES key. Another one, actually from Ishan, so my company. So it's 2 years old now. We managed to do such an attack on a mobile device. So it was a Samsung phone, and we managed to break the secret key doing the firmware encryption. Okay. So as you can see, they are all practical examples showing that such channel is possible. Okay. So I will try to together with you to see how it can be done. So here it looks like this. So it's a practical such channel setup. This is our setup in Ishard. So we're in Bordeaux, France, and we are doing this kind of attack in our lab. So actually, it's not a very complicated setup. So complicated. So what do you have? You have one oscilloscope. This is the most expensive piece because the oscilloscope needs to be relatively powerful. After that, you need to get an equipment in order to monitor as much as you can the chip activity.
Can I interrupt for a second? Your microphone is still causing a lot of distortion. Is there a way to? I'm not sure what the best way is to do it.
Okay, is it better like this, Jeremy?
A little bit. There's still some distortion. I'm not sure what the solution is, but
okay,
it's a bit distracting.
Is it better like this?
I think so. Yeah, just speak up loud.
Okay, let's use the built-in microphone.
Okay, thank you.
Okay, so what I said is, so you are reading on the oscilloscope. This is the most expensive piece, and after that you need something to collect the internal execution. So today, I would say the most powerful way is to use a near-field electromagnetic probe. Okay. After that, here we put a hardware bench in order to make some accurate measurements. Okay, so we have an XY table and some mechanics. And the most important thing is the software, where we can drive the equipment, correct the traces, and apply the statistics in order to retrieve the secret key. Good. So how much does it cost? I will make the distinction between identification and exploitation. So identifying is finding the attack. How I don't know anything about the device, and I need to find the recipe how I can attack the device and how I can find my way to apply successfully an attack. So obviously it takes more time and effort to make this identification. It's exactly the same thing in reverse engineering for a classical security flow in an operating system. The person, the expert looking for a flow can take months in order to find the flow. After that, the exploitation of the flow, once it's found, is very quick. So in such channel here, typically, we can say that an attack takes a few weeks in identification, typically. Okay, let's say 4 weeks, 3-4 weeks. The exploitation can be very fast. Or as I said, it can even be a few minutes. What I did actually, I try to put the cost of the equipment depending if you are willing to do an identification or an exploitation. So exploitation, you have to think how much it would cost to a hacker on the field. And you can see that the cost is very limited actually, because the hacker can use an open source project. After that, he can use an acquisition card, which is less than $1,000, and a set of probe that will be a few hundreds of dollars. Actually, it's 200, 300. You can even do yourself, your own one. So actually, all of us can do that in terms of cost. When it goes to identification, you will more have an equipment, as I showed you before. For the identification, you need to have a more sophisticated equipment. But as you can see, it's still affordable. It's more affordable for a company, less for anyone in the street. So we are talking about $25 kilo, $30 kilo for an oscilloscope, and high-end one. All the hardware bench and probes may cost 25 kilo euros. And for the software, I think the minimum is around 50 kilo euros to have a decent one. So all in all, we are talking about hundreds of kilo euro dollars. So that's not a massive investment, actually. Now, which IC can be subject to attacks? Which algorithm? So all cryptographic algorithms can be subject to this attack. And all devices can be subject to this attack. The only thing you need is an access to one of the side channels. So most of the side channel concern, I would say, physical measurements like power fluctuations, near field electromagnetic, as I said. But some recent work, showed that some devices have internal sensors, and if you have a malware collecting the information in the sensor, it can be a power sensor, typically. You can have useful information that can be sent via one of the communication interface, and a remote attack without a physical access to the device is possible. Okay. The name of this attack is cross-channel, and some paper named that a screaming channel. Anyway, behind the scene, it's exactly the concept I told you. Okay, so it concerns secure controllers, and most of the attacks so far were focused on the secure controllers. But now FPGA are also very much target, because FPGA can be used typically in military grade equipment. So it's very sensitive. And SOC device, so SOC standing for system on chip, are also subject to their biggest chip, a large piece of silicon, but still subject to an attack. So a typical attack is 4 steps. The first step is you need to collect the traces, okay? You need to get the information. And the information must be related to the internal execution of your algorithm, right? Once you have collected traces, because sometimes you need to collect millions of traces. Even sometimes initially we even collected billions of traces, okay? So it's a lot of traces, it's a lot of data. So you need to make sure that the information will be appropriate, and the signal processing is often required, okay, to make the data acceptable or appropriate for the analysis. After that, only on identification, you will need to make a leakage analysis in order to see, is my signal holding some useful information, okay? So you need to make an analysis to see how useful is your signal. Sometimes you have to look for this, particularly when you have a very small, tiny probe and you monitor an activity on a big SOC device. It's a bit like a big surface that you need to analyze. And sometimes you have to make sure you find the proper combination of the location, typically the location of the chip, and making sure that there is some useful information. And step number 4, you will use some mathematical statistical tool in order to extract the secret key from the tiny information that we can find in the data traces. So I will show you an example for all these 4 steps. So step number 1, actually this is an important one, of course, because this is where everything starts. The quality of the signal is tremendous, okay, in terms of importance for your attack. So here I put a video in order to avoid any demo effect. In particular, I am home tonight, so not in my lab. So here I showed you how typically an equipment can, this collection of trace can happen. So here we use some notebook from Jupyter Lab. And as you can see here, we work on a device. The device was not packaged. So sometimes it's better to package it, to unpackage it, or depackage it in order to be as close as possible as a silicon, huh? on top of the silicon. Sorry. You can be on front side or back side. Sometimes both are fine. And after that, yeah, we take all the equipment and we make sure that we can drive the oscilloscope, the camera. We can collect the trace from the oscilloscope, and we can drive the XYZ table in order to make sure that I will be able to find a better place where the maximum of useful information is. So in this video, you can see that here I am able to collect the data trace from the oscilloscope, and here I will be monitoring my stage. Here, you know, I move, and you can see on the top right picture that everything moves according to the joystick. Okay. So I'm going, we don't have so much time today, so I'm going to show you the following. So it's a long video. If someone wants to know more, actually this video, I can share it. And here I want to show you, okay, what we get out of this device in order to show you a live example. Okay, so here typically I'm going to pause. Okay, so as you can see, when we are taking a near field electronic probe and we put it on the right place on the device, there is a lot of information, and you can see this big pattern. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 for someone familiar with this is obviously an AES because there are 10 rounds. Actually, there are 11, but the last one is very tiny. So you have 10 rounds. So it looks very much like an AES execution. And actually, we have a clear idea where the different AES rounds are, and sometimes we can even go inside each pattern and understand the structure of the algorithm, like the sub-byte key, the shift row, and so on, which are the different operations that you can see in the AES. So as you can see, we can get information, but here I was talking information about the operation itself. Is it a XOR operation? Is it a matrix-based operation, or and so on? But on the data trace, most of the time, the data trace reflects the value that is currently processed at that time. And this is a very tiny information, and this is the operation that we are going to exploit after that. Okay? The second step is to process the signal. So as I said, to make it as suitable as possible for statistical analysis. So here I will show you an example. So this is trace, so I zoomed in, okay? And what I would like to show you, it's actually a typical structure of a signal trace. And if you zoom it, you can see that they are not aligned together. And actually, most of the technique, they would like every traces to be aligned together, which means at each instant of the algorithm correspond at the same time. Is how the statistic will work. Okay, so for doing this, we would like to move actually the trace so that they are as aligned as possible. Okay, and this work here, you can see a line here, but very quickly it's not aligned here and there. Okay, so there is a specific work to do in order to make alignment step by step. This work of alignment or signal processing may take 80% of the total time of an identification. This is the most consuming step of the attack sometimes. Okay, because actually you may face some jitter or dodgy or strange behavior of the device, and sometimes it requires some expertise and manual work in order to make sure that the traces will be aligned together all along the algorithm. Okay, so here I show quickly one example because each time is different. So here we do a peak-to-peak analysis. So we are here we define a threshold. We manage to define the different peaks. Each time we found a peak, there is a red cross, sorry. And after that, we do some pattern detection once we found it, which helps us to make a coarse alignment. And after that, we will take the pattern and do peak-to-peak detection in order to put everything in a proper place. Okay, so I'm not going to, here it's just an introduction. Again, I can spend hours to explain to you many examples, but it's how it works. So step number 3, you need to make a leakage analysis. Okay, so when the device is tiny and you have to put your probe on the device, okay, there is not much to explore. And when you have a sock and the probe has a resolution of 1 micrometer, okay, and the sock can be, let's say, 10 per 10 millimeters, so almost 1 centimeter. It's a lot of micrometers on the same device, so it can be a huge exploration. Okay, so for that, in Ishan, we do cartography. And I would like to show you one example of cartography. Here we go, it's there. So actually here it was a sock device. And as you can see, we explore only the square. I don't know if you can see on the screen, but we very much explore that part. And actually, on each point here, when I click on each point, I can see different, I would say, statistical functions that we applied here. For each point, we made a specific collection and we applied the statistics that you can see in front of me. So we were targeting an AES. And as you can see, sometimes here a t-test is a t-Welch test. It's a statistical tool. As you can see here, it's obvious like we have something interesting, right? Because here, I'm going to show you. We can see that the t-test is clearly highlighting an interesting activity. On top here, you have the average signal when an AES is executed. And here on the bottom right, you can see when no AES is executed. So you can see when there is a real difference, we can say, wow, we found the AES. So it looks obvious like this, but an AES can be 1 microsecond long. So this means that you have a big sock, a lot of micrometers, and actually in terms of time, it's very quick. 1 microseconds, and the current can be several milliseconds, right? Because a lot of codes is being processed. And when there is a hardware accelerator, it's super fast. So you can see that this is why we need this equipment and this software to make sure that we will be able to spot the right time and the right location of the chip. Because when we have it, we can do something. But if you don't find it, you will never get the key. Okay, this is where the identification time is so important. Actually, you need to characterize more or less your device against this attack. Okay, so just to show you an example, here is where the signal was beautiful. But if I move to another place, like that one, as you can see on top, average AES signal, we don't see anything. t-test, there is a bit of a tiny signal, but it looks like noise, right? As you can see, you need very much to find the proper combination. So here I'm moving my mouse here and there, just to show you different examples and show you where actually not so much signal can be found. And again, here I go where it's the brightest here. There is definitely a need signal. So there is something to exploit. Okay, so let's say that now we found the right place. We are confident that the AES execution is there. We managed to do the alignment, the signal processing, everything is suitable. So I need to find the way to attack. Actually, you have quite 20 years of research, of plenty of statistical tools, more or less convenient, in order to retrieve the secret from the tree set. And the strategy is a divide and conquer. What does that mean? Let's take an example of an AES. An AES, let's say that is 128 bits, so 16 bytes. The divide and conquer approach is the following. The secret is 16 bytes long. But when you are looking at the intermediate value processed by the chip during the AES encryption, some data will only be related to one part of the secret. Let's say 1 byte of the key. 1 byte of the key is only 256 potential values. So if I try to estimate, if I do a sequence of observation and I try to see this observation can only be achieved with this particular value of the byte, and just need to manage 256 possibilities and only one will be good. Okay? And if I do that for each byte, I can collect everything and I will find all the 16 bytes. Okay? This is divide and conquer approach. So here, a typical attack here, so this one is the most straightforward attack. Okay, so the most straightforward attack is, as I said, I apply the divide and conquer. So as you can see on my screen, I have 16 bytes to find. And for all 16 bytes, so 0 to 15, there are 256 possibilities for the secret keys. Okay, and for each of them, I would like to discover the outlier. The outlier will be my secret. Okay. So why is gray here? Because actually you have a statistical, you have the outcome of the statistical that we put all together, and we need to find one which would look outstanding. Actually, here it doesn't work because we cannot see any outlier. So I put in red actually where the base candidate here, and as you can see, the base candidate. No, sorry, I put in green, sorry, the expected key byte, which is AB here. And as you can see, this key byte is similar, or yeah, it's similar to the other. Actually, it's not an outlier. Okay. So this attack here doesn't work. Let's go to an attack that works. Okay. Looking at the time, I won't explain you that. Here is typically an attack that works. So exactly the same thing. I put my 256 outcome, and one needs to looks different. Okay. Here I put in blue my base candidate AB, but it will be in gray. That will be obvious that this one is different, right? So for the byte number 0, my key is AB, but for the byte number 1, it's C1. And the C1 is the one looking very much different from the other, and so on and so on. So I do actually 16 attacks. Okay. And for all of them, I was able to find the outlier. So I can reconstruct the whole secret AES. And that takes a few minutes when it works. Okay. So you may ask, okay, but what is this graphic on the right? Actually, this graphic on the right, it just takes the maximum values as you can see on the left, but using more or less measurement. So here, on that case, I have 1,000 measurement, 2,000 measurement, up to 5,000 measurements. Okay, so here you can see that the outlier on this byte number 13 started to be an outlier after, let's say, 1,400. Okay, so I needed 100 and 400 measurements to retrieve the secret. Practically, I may need several thousands, but sometimes I may need several hundreds of thousands measurements, or even more, millions or dozens of millions. It really depends how much device leaks, how good is your physical measurement. Okay, good. And what I would like to show you is there are plenty of statistical tools after 20 years of research. So here is what comes with one tool. Okay, and here this is the very same measurement, exactly the same input, but it's another tool. That one is working much better, as you can see, because the outlier is so obvious. Okay, as you can see, it's even more obvious than previously. Okay, and I can move, and this is the same for all the different bytes. Okay, so for your reference, this attack is named linear regression attack. Okay, and the previous one was what we name a CPA for correlation power analysis. Okay, good. So I have my secret. Okay, it took me maybe 3-4 weeks to identify, and it takes me a few minutes to exploit. So I'll try to see how harmful it is for a system. This question I cannot ask. There is not a single answer. Obviously, it will depend on the system. Okay, so I only put some insight here. If this is a symmetric key like an AES, the typical usage of an AES, but it's not the only one, is the encryption. So if you manage to expose the secret key, you will expose the data that were encrypted. You will be able to decrypt them. Okay. So it could be more or less harmful for your system. So there are some mitigations. So first, you can manage, there are some cryptographic protocols, and you can try to make the keys ephemeral. Okay. It's important typically. So ephemeral, what does that mean? Is there will be the key will be used only once. Okay, so we name them session keys. Okay, so it's not always possible, but it's a potential mitigation when you have when the system allows it. Okay, but you really need to think about something for symmetric key. Ephemeral keys. Okay, the stake is not very high. A master key, which is a key that is not changed on the same device during all the lifetime of the device, can be a bit annoying. But the worst is the same key shared across many devices. Just to give you an example, the Samsung phone that we broke a few years ago, so we broke the firmware encryption. The key was shared across all Samsung phone of the same, the same Samsung phone. It was a Galaxy S or something. So what does that mean? Is if I manage to find the key on one device, I can break all devices. Okay. So if the key is unique per device, the stake is not the same. Okay. And if the key is ephemeral, it's even lower. Good news is it's possible to protect as well against this kind of attack. So I put such a resistant implementation. So the principle of these protections is more or less how to make the internal execution different from the real value that the hacker will try to estimate. Okay. So for that, you can use random values, and there are different techniques, but it will require another talk to talk about that. For public key, I'm talking about RSA or elliptic curves. A typical usage is a signature. So the impact when it's compromised, when a signature is compromised, you have a malevolent ID usurpation. So this is obviously not good, because signature is to make sure that we know who is doing something. So if you break this, it's bad. Mitigation here is to make to make sure that the implementation is such and resistant, and it's possible. So my conclusion for today: finding the recipe identification, I think you understand, is seldomly quick and easy. So if you have really much very leaking device and small device and so on, okay, it can be possible. But when it's about a SOC or modern device, our experience is that it's never simple. What does that mean? Not simple. It takes the usual time. It takes weeks. Okay. Multiple expertise are needed. Yeah, you can have someone very good at collecting trace or for the signal processing, and another expert in statistical operations, or making sure that we are in a good operating condition to collect the trace on the device. And different techniques also need to be developed as well. But once the recipe is found in terms of exploitation, it's not necessarily a big deal. Okay, that you can even do in your garage most of the time. You can find the secret in a few hours or in a few minutes, depends. And the equipment is affordable. So, in my opinion, it's a strong opinion, but security protection against such an is not an option. When you design a chip and there is cryptography, please consider such a protection. Particularly when, because the lifetime of a chip on the field may be long, and you cannot update the hardware easily. Okay, so the mitigation should be implemented, or must be implemented at the hardware level first, and additional protection should be implemented at the software level. Okay, good. Are you ready to take your Satchel on board? You can. So you can contact us if you want. Well, the first thing is we have the ability to audit your solution. So a lot of customers are doing that and asking that to us. So we have the expertise, we have the lab, and we can do that. You can also learn by doing. So we have a set of practical training. They are online, so you don't need to travel, and we will show you step by step how to do this. There are individual practical training. It's perfect for beginners. And we have also a set of training for experts, because we are never fully expert and we always need to improve ourselves here and there. And if you want to create your expertise, we can help you to build your lab and make sure that you have an operating lab in your company, in order for you to take this, to have this expertise, to control this expertise in-house, and make sure that your product, you will be able to qualify your product, and particularly to qualify their resistance, and make sure that if it's not enough, you can improve the quality of your product. I hope that you're still awake, and I hope that you enjoyed this talk. And I think it's open for a few questions.
Yeah, thanks, Hughes. That was pretty interesting. So there's a couple of questions that came in, but let me ask you my question, maybe. Yeah. So clearly devices can be compromised. And if these are connected devices into a network, you know, that network could be a power plant, it could be a gas line. How do people go about trying to protect against this kind of attack?
So for this particular family of attack, you need to be close to, or you need to have an access to one of the sidechain of the device where the secret is processed. So if you take, I don't know, a network and so on, generally speaking, you don't have an access. You don't have a remote access of the algorithm itself. Okay, so this makes the attack more difficult. But like the Google Titan key is supposed to secure a cloud, right? It's the meaning of this. So when you have an access to this key, here the Titan Google Titan device, it was possible. So it's all a question of how much you can access. You can get an access of one of the sidechain, and this can be a limitation. And I think, sorry, I think it will be a bit painful for the eyes of everyone, but I would like to emphasize that because I think it's important. I think the attack requires physical access to the device, but you know it requires here the physical attack, physical access. So it's not always the case. So for network, it's more difficult. So you may more think about other attacks like you want to protect a military device, or you want to protect a payment device, a smartphone. Here you can attack this device because you have a physical access.
Okay, interesting. And one of the other questions that came in: what are the most common attacks that you see?
In sidechain, what is the most common attack? Actually, the basic of the basic is what we name the correlation power analysis, but it's the statistical tool, okay? Used at the end of the whole process, okay? So this one is the most common one. But today, more and more deep learning is being used in order to make more sophisticated attacks and even break some of the countermeasures that were enough beforehand and that are no longer enough. So it's a bit a race, you know, between the hacker and the secure developers. But it's always the same thing in all security challenges.
Okay. So there's two questions came in from Rosita Temorzadeh. First question is, how do you distinguish leakage after the signal processing? And the second question tied to that is, aligning the traces is kind of a brute force approach. Is there any kind of smart algorithm that can optimize both the length of time and the calculation complexity?
So what was the first question? First,
so the first one was, how do you distinguish leakage after the signal processing?
Okay, let's take that one. I use a t-test. Okay, so a t-test, it looks like a crazy word, but a t-test is specifically, imagine that you have one key, it's secret, and you have the ability to send your own message. So you ask the device to encrypt. Okay, so you have the control of the input message. Let's say that for 1,000 measurements, you will always send the same message. And for another measurement, you will send only random values. You take these two families and you apply some statistics. So you try to compare actually both. If something appears, between both after the statistical operation. This means that you have a useful information. This is how it operates, okay?
Got it.
And this is how you can make your leakage analysis. So I really try to make it simple, but we have some specific training where actually you use very much the statistical tool, and you can see on a real set of traces how it works. After that, it looks like a brute force. I wouldn't say it's a brute force. It's just aligning the time of the algorithm with the real time. So because as you can see, we try to estimate, let's say, one specific value during the algorithm. So if we want the statistical attack to work, all the time where this intermediate value is being processed, they must be aligned together, okay? But the thing is, we don't know exactly this time because it's a kind of a black box approach, right? We don't know exactly when this value is executed. So this is why we need to align together the whole algorithm in order to make sure that you won't miss the point, okay? And you make sure that everything is aligned together. So at the same time, you have the same variable processed for each execution, for each different measurement. And that takes time. So I have been doing a lot myself. It can take 1 week, or because it's a trial and error approach. It doesn't take 1 week by itself, but you try something, you don't want, it doesn't work. Okay, you try another thing, it works a bit better. It's a trial and error approach.
So I guess the question, clearly a lot of the semiconductor companies are taking mitigation steps to try and make the system more robust against this kind of attack.
Yes.
But is it just a matter though, the processing is going to get easier and faster? So there'll be a chicken and egg. There'll be an improvement in mitigation against attack. Then the attackers will get more sophisticated.
Yeah.
This is a kind of arms race that's going on.
But so far we didn't touch the boundary. It depends. Obviously, it's a bit like any protection, huh? But if after that, it's a question of risk management, I would say. So, how difficult, how much acceptable it would be to say, here I can accept the risk. Okay. So typically there is actually a metric. It's named GIL, J-I-L, that gives a rating to an attack. And today the industry is typically saying that when the rating reaches 31, and 31 is reflecting the complexity of the attack, the different effort in terms of equipment, time, expertise, and so on. If it reaches 31, it is considered as acceptable. We say it's resistant to a high attack potential. And this is maybe the main answer to your question, Tom. It's the idea is not to get to a zero risk. The idea is to go to an acceptable risk. And yet it moves along the time, but it doesn't move super fast. So it's manageable. It's how a lot of device manufacturers manage to have secure devices in the field.
All right. Okay, thank you. Well, I think at that point, we'll hand back over to Jeremy.
Yeah, thanks, Tom. Thanks, Hugh. There will be some time for some additional questions, but I think we're at about an hour mark here. So I wanted to go ahead and do the raffle drawing. So we've actually done the drawing already, and our winner is Daniel Langton. So congratulations, Daniel, for winning this multi-tool hammer, and I'm sure you'll find it very useful. If you could send an email to me at jeremy.toll@wca.org, or you can put your contact info into the chat box directly to me. That would be useful, so then we can get that sent out to you. So I appreciate it, and I appreciate everybody's time here. Tom and you, do you guys have more things you'd like to discuss?
No, I think we're okay. I think I
Okay,
don't see any more questions coming in.
I
okay,
have just 2 words. Thank you.
Thank
yeah,
you.
thanks for a very informative presentation. I learned a lot, and hopefully the audience did as well. So look forward. Okay, I got Daniel's contact information. Great.
Good.
And we'd like to wish everybody a great day and a great holiday weekend in the US for Labor Day. And please join us for a future event. And we're very excited to have events like this and keep it going.
Guys.
Thank you.
Thank you. It was a pleasure. Bye-bye.